a comprehensive basic understanding of KS5 advanced capacitance, which is a pivotal part of AS and A2 physics, and it links very important chapters such as AC theory and electrodynamics, which is the conventional electric current physics. So please try to understand that we know that in a normal framework, the normal regular framework, which doesn't include electronics, we are dealing with metals, D block elements, tungsten, vanadium, iron, lead, hydrogen, copper, platinum, palladium, gold, silver. All the D block elements, they are not non-metalloid, they're not metalloids, they are pure metals, and they exhibit metallic characteristics both at the atomic orbital level and at the physical level, where they have properties such as they are sonorous, they are good conductors of thermal and electrical energy, they conduct heat and electrons very, very efficiently via molecular vibration and electronic acceleration. They also are sonorous, shiny, ductile, malleable, have high melting points, boiling points. They melt to conduct electricity as well, and they are a great facility. So all of the so we know that the overarching principle that governs the electrical conductance and conductivity, resistance and resistivity, conductance and conductivity, resistance and resistivity. For those who've known these concepts, they know why I'm naming them differently, and all of these four quantities have separate formulae. They are governed by the overarching principle of ohmic induction. Ohm's law, which states that the PD applied to a circuit is directly proportional to the resistance therein, and that resistance comes from the wires. Like, for example, if you had a germanium or a copper wire, it'd be far less, and silver wire far less. But if you had a platinum or a tungsten wire, that'd be far more higher. But if you and it also comes from the resistors connected in series and parallel throughout the circuit. So we have to realize that the overarching principle is ohmic law, ohmic conductance, and then we need to find out how to quantize the moving or the stationary charge in the circuit, which is an expression of the current and expression of electrical energy, P equals IV. So we need to find out how to quantize the moving charge through the circuit. The charge is moving, the electrical energy is moving, but the electrons stay in their place. Otherwise, the electrons would have gotten consumed. Having said that, I showed you in the previous video, a few videos ago, how to derive the time constant for the capacitance. So if I use this and plug it here, if I plug T equals RC into T of Q equals IT, I get this. So this is how we got T equals Q over V, because of this, because of this, because of this. And yeah, so hang on, I'll use this later. So this is where C equals Q over V comes from, C equals Q over V. Now, we know that work done is calculated in mechanics, thermal physics. It's also calculated vigorously, vivaciously in other branches of physics as well. But when it comes to capacitance, electrical energy, or just purely capacitance, the work done by the charge or on the charge needs to be quantized. And so these are the four formulae we use: W equals QV, CV squared, Q squared over C, or that's the work done. And then when we need to find out the energy, we just halve it due to the RMS convention, root mean squared convention, and that is enough to explain what I've just said. And this is how we quantize the work done on the charge by the charge, and we also find the energy, the capacitance energy, by half equal. So the units for this is joules, 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 and we know that for work done for electrical energy is I squared RT, or V squared over RT, V squared over R into T, and then PT. So we need to what I'm trying to tell you is that it's very simple, straightforward. You need to understand this formula, and then this and this and this, and the rest will be easy. And you can just then play with these formulae and just substitute them around to get your answers as smoothly as possible, without any friction, negligible friction. So I've drawn a circuit here. So this switch, when closed, will allow the battery to be utilized and the current to be quantized and the resistance to operate to give you a voltage. And as a function of all these components, capacitors connected in parallel will begin to store energy. Now, capacitors are of about 6-7 different types. I'm only using this plate, a parallel plate capacitor. I'm not going to talk about the cylindrical or the spiral or the sheathed or the insulated capacitor. I'm only going to give you a simple understanding of the basic model of a capacitor. And most capacitors fall in this category anyway. So there are about 6-7 kinds, ranging from the very advanced to the ones used in laboratory for quantitative purposes for post-16 students. Experimental quantitative purposes for demonstration to post-16 students. And the reason I've drawn this circuit is because, just to let you know, that similarly to resistors, capacitors are calculated as well. The capacitance is calculated in a similar manner to resistors, and the capacitors in parallel are calculated like the resistors in series, and vice versa, which means that capacitors in series are calculated as resistors in parallel, and capacitors in parallel are calculated as though they were resistors in series. So capacitors in parallel are calculated as though they were resistors in series, and capacitors in series are calculated as though they were resistors in parallel. I hope it. And why does it happen? It's because of T equals RC, because resistance is inversely proportional to capacitance throughout the harmonious equations that we find here. So it harmonizes as an inverse proportional relationship. So please try to understand the funny part of the capacitance, that they're opposite to resistance, they're inverse to resistance, hence their calculations are inverse to resistance as well. Now, first of all, whenever a capacitor charges, it has to discharge. Charge, discharge, charge, discharge, charge, discharge. And the equations for discharging are as follows. So you can calculate the voltage or supply voltage stored, or the potential of a capacitor to store a certain amount of voltage, by calculating the voltage you supply and then the time supplied, divided by the resistance times the capacitance, the value of the capacitor, which could be in picofarads, nanofarads, or microfarads. Microfarads is the largest that's used, because milli and a simple 1 farad is a huge amount of charge. And then when the current is being calculated for its discharge, you'll have to put a negative sign here, because it's a depletion of energy and current is an expression of energy, E equals IVT. So and there are certain complex mathematical reasons as to why you'd put a negative sign here. So when discharging, it's voltage of the capacitor equals voltage supplied exponent minus T over RC, which is torch, or equals a time constant. And when it's the current, it's negative I exponent T over RC, and then this is the summative equation, which is Q supplied, the Q of the capacitor, total charge cumulative in the capacitor. It would be a product of the supplied capacitor charge exponent time supplied over RC. So again, I'm going to go back to these formulae. Please, whenever you are solving these equations, these exponential equations, you have to keep these in mind, because capacitance is a chapter that links electrical energy, the conventional electric theory, a bit of electronics, AC theory, and electric field, electrodynamics, electrostatics as well. So please keep all of those 4 chapters in mind, and synoptically assess the questions on capacitance as you go through and as you do your exercise. These days, the modern questions are quite simplified, and but they still test your pedagogical understanding of the chapter and its synoptic relation to other chapters. So W equals QV, Q equals IT, C equals Q over V, Q equals CV, E equals F over D equals V over D. This is what you need to keep in mind all the time. And then W equals half QV, half CV squared. And now we come to charging and discharging again. And so now that we've understood charging and discharging and the equations for it, we'll now discuss the charging aspect. The charging aspect is here. So when you're charging, it's a little bit more complex. So it'll be the total capacitance, the total voltage of the capacitor equals supplied voltage exponent 1 minus T over RC. Why? Because the mathematical rationale for charging equation is due to E's value, E exponent 1 being 2.7 and exponent nil not being 1. So in idealistic circumstances, which is theoretical circumstances, the supplied voltage would be far greater than the capacity of the voltage to be stored in the capacitor, but therefore not feasible when you integrate the equation, because the template for this equation is y equals x naught exponent 1 minus a over b. This is the model of this equation, and that's a decay rate equation model form. And so the current this time would not have a negative charge, and the charge would not have a negative charge either, because in the previous condition of discharging, current had a negative charge. Now, like every graphical analysis, this is the charging voltage, charging current, and charging charge accumulation, coulombic, and then current, and then the voltage. Like every exponential equation, graphical analysis, you have to lineate the equations. You have to lineate this, which this is how you lineate a current when you're calculating the current potential, the current accumulation or discharge, and the voltage discharge, and then you'd come to the discharge of the charge. So you stick log naturals in there, and then you decompose the equation, and then once you're trying to calculate C, Y, and M, you have to inverse natural log the quantity to get the C, to get the Y, and then this will be your gradient, which is M, and the K will remain constant because time doesn't change. The time taken would almost always remain constant, and may change a little bit if the capacitor material deteriorates. So conductivity, conductance, resistance, resistivity are all very, very relevant to capacitors, because of the material limitations of the capacitor manufacture standards. Having said that, I hope it was useful and you were able to derive a pedagogical understanding of the chapter of AS and A2 capacitors. Now, what will happen is, typically speaking, what they do is the first questions will all be about, the capacity, this much capacitance, this much charge was in a circuit, and on a voltage of 60 volts. So how much energy has been transferred, or they will ask you to flip through these formulae and use these formulas to get your answer. So sometimes they'll have a circuit and the current is missing, but the voltage and the charge has been provided, so they might ask you to calculate the time. And sometimes the voltage and the capacitance has been provided, so they'll ask you to calculate the current by giving you the time. And so they'll make you run through all of these formulae. And the energy questions will sometimes capacitance energy questions will test you by giving you one value and missing the other one, and then asking you to indirectly calculate the third value by giving you the two values. So I hope I understand where I'm coming from. And so in questions like V equals what they'll do is they'll say, okay, so if a capacitor has a potential of 1,000 volts, and how much voltage needs to be supplied per second for it to, in a circuit of in a circuit of 20 ohms and a voltage of 20 ohms, 20 volts. So what they'll do is they'll give you this. So you'll have to do 1,000 volts equals 1 minus. You'll have to put 1 second here, and then the 1/400, and that's how you'd have to find this one out. Now, you can't do this just there and then. What you'll have to do is to take all of this here. So it'll be 1,000 volts divided by E1 minus 1/400, and that's how you'll be able to find this one. So this is a bit complicated. Now, if I were to stick natural logs, it might make your life easier a little bit, just by a little bit. You'd have to one way is to do this. This is one method, and the other method would be to but that would complicate it. See, if you have to take a natural log of all of this, you'll have to bring it back. Because of mathematical substitution, it'll be written in the form of this form. So it'll be plus so this is how you'll have to write it down, and I wouldn't recommend that. I think this method is far easier, because a lot of people with weaker mathematical understanding will not be able to resolve or justify this. They won't get their head around it. So unless you've done engineering mathematics, don't use it until you've got a sound understanding of exponential, advanced algebraic maths. So again, the units for this will be volts, amperes, ohms, coulombs, amperes, seconds, coulombs, amperes, ohms, and farads, microfarads, picofarads, nanofarads, and for this one it'll be coulombs, amperes, coulomb, amperes, ohms, farads, coulombs, voltage, farads, coulomb, voltage, ampere, voltmeter, ammeter, voltmeter, resistor, capacitor 1, 2, 3, battery, switch, and this will be ampere, seconds, ampere, ohms, and so it'll be half Q squared over C, half CV squared, half QV, or W equals QV, CV squared, or Q over C. So it has to do with the work done on a charge or by the charge. And this is how you decompose an exponential equation for discharge of a charge in a capacitor, by separating it. And so you'll have to lineate it, and you'll come up with a constant, a gradient, a y-intercept, and a y-value. And then you'll have to do the same to the discharge of the current, the amperes, in a capacitor, and you'll have to come up with the y-intercept, the y-value, the intercept, and the gradient. And you'll have to do the same for the discharge of the potential in a capacitor as well. So once you've done that, it'll be the more practice you do with the questions, it'll be far more easier for you to understand and grasp the understanding of it. Now, if you have to decompose one of these equations, the charging equation, it'll come out in this format: log natural capacitor, voltage of the capacitor, and then 1 over RC minus 1 over RC times T, which is the time, plus log natural supplied voltage plus 1. And again, just look at these questions, these equations one more time. So that's W equals QV, and then IT, C equals QV, and then electric field equals F over Q, V over D, and then half QV, half CV squared. This is for charging, for current, charge, and for voltage. This is the discharging graph and the charging graph, and that's how things are. The rest are questions that I will do in future video. For now, I think this will be a very nice, fine, summative, brief, pedagogical, dissective introduction of the ASA2 capacitance and how it links with other chapters such as AC theory, Hall effect, the electronics chapter, and the regular electricity chapter of A2 physics. Thank you very much for watching this. I truly hope you learnt something through this video, and I apologize for all the media and technical difficulties I experienced, or which you may experience, because I'm holding the phone in one hand and broadcasting from the other. And if you have any questions, please do not hesitate to post them down below. I'll try my best to answer them. Thank you very much. Have a lovely day. Take care. Bye now.